Hi everyone, I am Deepika and my research title is Towards Structured Multimodal Understanding, Scientific Diagram Captioning with Modern VLMs. Scientific diagrams are very different from natural images. They rely on a structural, symbolic, and spatial reasoning. This includes understanding arrows, labels, part-whole relationships, and multi-step processes. However, current vision language models, which are mostly trained on natural language or natural image dataset, struggle with these diagram specific skills. They often fail to correctly ground labels, decode symbolic arrows, and or interpret relational chains present in educational and scientific diagrams. The second challenge is that existing benchmarks are designed for natural images, so they do not properly evaluate diagram specific abilities like grounding, label comprehension, and relational reasoning. And in this work, we address this gap by benchmarking 5 modern VLMs on 4,908 scientific diagrams from AI2D caption dataset. Our result clearly highlights that both the strengths and the limitations of current VLMs and show why we urgently need structure-aware, diagram-focused improvements in next-generation multimodal systems. This work uses AI2D caption dataset, an enhanced version of AI2D with 4,908 scientific diagrams across domains like biology, astronomy, and engineering. Each diagram includes human written explanatory captions, structured elements such as labels, arrows, and flows, and semantic tags from original AI2D dataset. And the dataset has been split in 70% training data, 15% validation, and again 15% in test data. And this entire dataset is publicly available on this GitHub link. This is the framework that shows fine-tuning process of instruct bleb. For other models, we followed a similar process with adjustments based on their specific architectures. Here we can see that the diagram first goes through this vision encoder. Most early layers, as we can see here, 0 to 8 layers, are frozen while the later layers remain trainable. And the embeddings along with the query tokens then pass into the Q former, and its output go through a projection layer, as we can see here, and are combined with the text instructions before being fed into the LLM. And this way the model produces a generated caption here. And this table shows the fine-tuning configuration we used for each model. For most of the models, the early vision layers are kept frozen, while only the higher layers are trainable. For example, in instruct blib, layers 0 to 8, we can see here, are frozen, and 9 to 11 are fine-tuned. And different alignment modules are used depending on the model. Instruct blib relies on a fully tuned Q format, while others uses MLP projection layer, and some are trainable and some are frozen. And on the decoder side, we applied LoRa adaptations for efficiency, except in this Polygamma 2, where we performed full decoder fine-tuning. And these are the results. Here we can see that InternVL 2.5 stands out, achieving the best score on Blue, Meteor, Cider, and Spice, which shows strong semantic and structural understanding. While this Polygamma 2 leads in CLIP score, which indicates better alignment with vision language embeddings. Whereas in this zero shot versus few shot comparison, we see that Polygamma 2 performs best. And this plot shows the CIDR score trends across different training supervision levels, starting with the 0 shot setting, Polygamma 2, which has been shown in this red color. Polygamma 2 performs the strongest, while other models lag behind. But as we move to few short training, all models improve. But in the fully fine-tuned settings, in turn VL 2.5 shown in the green color here achieved the highest CIDR score overall, uh, and followed by Polygamma 2. Thus, we can say that Polygamma 2 generalized better in zero shot, but in turn VL 2.5 benefits the most from fine tuning, which makes it a best performer for diagram captioning with supervision. And here we can see, if we talk about conclusion, that in turn VL 2.5 delivers the strongest overall performance, while Polygamma 2 excels in low data setting. Yet key challenges remain, especially spatial reasoning, label grounding, and structural alignment in scientific diagram.